Hello. Okay. Today, this is Stat 3050, but totally optional stuff. Today, we're going to go over decision trees, decision tree regression in this case. It's just another form of regression that has a couple of special tendencies and sort of more lax rules than regression, but there's also a few other things that are much different than traditional linear regression. So there's a lot, there's a ton going on in this. And so I want to make sure that everyone understands that it's not totally necessary to understand. And that I'm also, I'm a statistician right now and not a data scientist, at least professionally. So there's some things in here that I probably will leave out that a true data scientist will maybe be upset with. But I'm going to show you the sort of gist and the general idea of decision trees. So there's going to be a few things that I'll say, hey, this is different than regression. Just make sure that you sort of set them aside from each other. They're not the same thing. A lot of the rules are much, much different. So just sort of keep that in mind. Try not to get confused with old regular regression, because that's what I care about the most, at least for this class. So let's get into it. I've got another script open off screen, so I'm going to be doing some copying and pasting here. So the first thing that I want to do, I want to set my working directory. And so I'll just do that. Easy peasy. And then the next thing, very important, we're going to set the seed. What this does is that when we start randomly generating numbers, this will randomly generate the same numbers over and over again. I recommend that if you are doing this side by side, I would recommend using the same value here, 3050. It's the class number. But this is just going to make everything the same for us, because we're going to be doing some random sampling. And if you don't have the same seed, the same set seed, then you're going to get differently random sampled values, which will change the output just a little bit. But we'll just leave it at that. So the next thing is that we're going to load in the required libraries. You should be familiar with two of them, the Tidyverse and Ggfortify. I'll just use that briefly. But then we have this library tree, and that's where we're going to be doing a lot of our regression trees from. That's the library from which they come. So let's read in the data. The data that we're working with, read in data. The data that we're working with is pretty cool, I think. Let's take a look at it. So what this is grad school admissions and sort of the chance at being admitted into grad school. Not whether or not they did, just the chance of it. So the way they calculated this is actually kind of complicated. They use what's called logistic regression that kind of fits probabilities of some event happening, and then they sort of back transformed it and put it back into linear regression. Again, not super important to understand how they did it, but we see that we have the chance of admit and then a bunch of different other variables here. So GRE, everyone's familiar with that. The TOEFL, that's like a language test. Purpose statement, so like the essay that they write, whatever, that's on a scale from 1 to 5. Letter of recommendation strength, that's also on a scale from 1 to 5. And then the GPA, we're going to fix this. Right now it's on a scale from 0 to 10, which is not helpful. We'll put it back on the 4.0 scale here in a second. And then research, whether or not they did research in undergrad. Okay, so we have all of that. We're trying to figure out what's the probability of them getting into grad school. So the first thing I want to do, I said earlier, I'm just going to kind of redo that GPA value here. So I'm just taking grad, taking the data from grad, and then I'm mutating it, and I'm just renaming it the same thing. So it just replaces the column rather than makes a new column, and then putting it on the 4.0 scale. So if we do that, I should probably read in. I should probably read in the libraries first. Cool. Okay. Just for a note, for clarification, this pipe operator, percent greater than percent, that's part of the tidyverse. It's not a base R notation. So again, that's why it gave me that error. So now let's run a summary on grad. And now we see that the max GPA is 3.96. The minimum is 2.7. So that's all good. And everything else here looks all right too. Okay, so let's try a linear model. I'll go ahead and tell you that it's not going to work. I'm actually just going to copy and paste what I have written earlier over, so you don't have to see me do all that. And the idea here is that we want to have all significant predictors because we're trying to predict the probability. We're not trying to figure out sort of the relationship between the two. We are actually trying to make a model that is used for prediction. So I've left, doing this a few times. The purpose statement strength doesn't matter in this case for the linear regression model. So I left it out. And then we see here that everything is statistically significant, and that's all good. But what we need to check is the residuals. Okay. So I'm going to use that autoplot function. Just going to copy and paste it over. I'm going to run that. We'll zoom this in just so we can actually see it a good bit better. Okay, so the residuals do not meet our assumptions for linear regression. They're all fine over here, but as we get further in, we see that there's some clumping on this side, maybe a tiny bit of curvature too. So what this means, and it kind of makes sense if you think about it, the nature of the data. Everything here is sort of on like an ordinal scale, almost, meaning that the higher values that you have, the better, right? So if you score really high on the GRE, it's likely that you'll get into graduate school, right? Same thing with GPA. The higher the GPA, the more likely it is that you're going to get into grad school. And so that's what we're sort of seeing here. As the values increase, they do start to fit around the line much better, right? Which just kind of makes sense, right? The higher the values are for all of these things, then the higher the probability is going to be. And we see that there's more uncertainty when you have lower values for those predictors. There's nothing I can do to this. I've tried. There's no log transformation. There's no ulterior or alternative transformation. I've tried everything. I've tried advanced transformations. Nothing worked. Interactions, nothing helps. So we're sort of out of luck with regression. There's really not much that we can do. So let's try a different version of regression. Let's try a more sort of advanced model. So with this regression, linear regression is what's called parametric statistics. Okay, and what parametric means is that it sort of assumes or kind of requires that the residuals of the model that we're making should be decently normal, capital N normal, with a mean of 0 and a standard deviation of 1. And we don't really see that here. And let me do this. Whoa. We see that the residuals are fairly skewed off to the left, right? There's a huge tail over here and not so much of a huge tail on the other end. So it's not good. It's not good for us. When we move into the decision tree, in the decision regression world, that's what's called nonparametric statistics. And statistics sort of is used in quotation marks there because we're not really doing statistics, more or less, because we're not really doing a whole lot of intense math, like calculus and whatnot. What decision trees do is they actually just do a ton of algebra, and they use more or less algorithms to sort of come up with a model. And the math is actually very digestible if you want to go look at the sort of documentation or the theory for decision trees. It's pretty interesting, I think, but it's very difficult to do by hand. Whereas regression, theoretically, it's a little bit easier. Okay, so let's get into trees. Let's go climb some trees. So I'll do this. The first thing that we need to do, and I'll type this out just so we can kind of see what's going on. And we can do this for regression too, linear regression, but what we want to do is we want to make a training data set and we want to make a testing data set. When we're working with regression, we can also do that. We can split the data up into what's actually being used for the model and then what is sort of more or less the testing, what we're going to use to predict or at least see the strength of the model. We can do that for regression. That's not really the point of regression a lot of the time. Most of the times it's used for just relation, trying to figure out how one variable affects the outcome. But that is not, the purpose that we have right now. So let's make some training data. The first thing that we want to do is that we actually want to use, or we want to make a vector of values that are randomly sampled based on the data set that we have. And so how am I going to do that? Great question. What I'm going to do is I'm going to say train, and then I'm going to put an equal sign. Okay, so the equal sign and the arrow, they both do the same thing, essentially. This arrow is a little bit more specific, and we'll look at the type of data frame or vector or whatever that you're looking at or trying to make, and we'll give it sort of that description in the environment. If we just use equals, it's just going to make a vector, which is fine, which is good for us because all we want to do is make a vector of random numbers that's going to be used to sample the data set. So we've already set the seed, so that's good. Stat 3050. Let me run that actually just to make sure. So that we all get the same random sample of values. So we're going to use the sample function, and that's going to take a few things. The first one is x, so that's just going to be 1 through the length or the number of rows of our data set. So if I just run this, what it's going to do is just going to print 1 through 400, right? So this is just the sort of generalized form of it. We can also just do 1 through 400. It would do the same thing, but I don't want that. So this is the thing that it's going to be sampling from, a list of numbers 1 through 400, okay, or the number of rows that we have in our data set. And then the size that I want to sample is about 80% of the data. That's sort of the convention for making a training data set. You can do less, you can do more, depending on the size of your data set. We have 400 observations, so we can get away with having sort of a bigger testing data set than we do with a smaller data set. That's fine though. So how am I going to do that? Well, I'm going to use the same n row, and I'm going to put the grad in there. So n row just looks at the number of rows in our data set. If I were to run that, it'll just print out 400 down here. So I want to do 80% of that, so 0.8. And if I were to run that just by itself, we would see that 80% of 400 is 320. Okay, so that's all fine. This is just shorthand, making sure that we can kind of reuse it in the future, right? Okay, so if I just run that, if we look over here in the environment, now we see a vector of integers 1 through 320. 320. There's 320 values in here, and they're all just random row numbers. Okay, and then what I want to do is I want to make a testing vector. Okay, so that's just going to be the opposite. That's going to be all the negative values of the training. And so you'll see over here that we have 61, row 61 essentially for the training, and then the testing is going to be everything that is not that row, and it'll do it again and again and again for all of the values that we have in our training vector. Oy, okay, so that's just the vectors, right? That's just the random numbers that we want to use to actually sample the data set. We have not actually sampled the data set. We've only made the vector of numbers that will grab the random row numbers. Okay, cool. So let's make a training data set. And it's going to look like this. I'm going to call it training data. I'm using the arrow now because I want it to be saved a little bit more specifically as a data frame. And then we're going to use the square bracket notations, right? So this is my data frame of the original data, and I want to sample the rows. I want all of the columns, but I just want to make a new training data set based on that vector of values that we have for the rows, right? And then I'll leave the column option here blank, right? So if I run that, now we see that we get 320 observations of 7 variables in the training data set. We'll take a look now, and we'll see that, hey, check it out. The training data set is saying take row 61, 274, 276, blah, blah, blah. And then this is what we get, row 61 here, row 274, right? So we can even go back into our original data set and look. So let's go find row 61. It'll be exactly identical, so it's a GRE of I guess 309. Scroll down to 61, and there it is, right? 309, 100, 3.0, 309, 100, 3.0, right? So that's all that's done is just sampled the row numbers and then made a new dating set, a new data set out of that. And then we have our training data. We need to make our testing data too. And we'll just do that the exact same way, except instead of train, we'll just put test in here. And now we see that we have the rest of the data left over, right? So 80 observations of all of the rows that are not in the training vector. Oof, okay. Again, you can use this. You can just copy and paste this in your future studies or research or whatever, and you're all set, right? Just change this. So I'll even make a little note here. This is the sample percent, and this is just the number of rows. Cool, 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 cool. All right. Oh, yeah. So we've made the training, and testing data. Now we actually want to make the tree-based models. All right. So we're going to start off with decision trees. And I'm going to call my model, I'm going to call it just tree model, and it's going to get this function tree here, and then everything is the same that we've seen in regression as far as all the arguments in here, so it's just formula, and then our outcome, chance of admit, and I'm going to include all of the variables because now we're using a different type of regression, we're using a different type of modeling, so it might even turn out that the one that we kicked out, the letter of recommendation, I think, or the purpose statement strength, it might actually be, a decent predictor. And then the data is not all of the data. We just want to use the training data. So that's all good, and that's all fine. Okay, so just like always, we don't get anything initially. If we were to just run the tree model, what does this look like? Not good, right? Let's just take a look, and we'll get some terminology in here in a second. So we have node, split, n, deviance, and then the y value. Okay, and then the asterisk here represents the terminal node, not statistical significance, because we are out of that world. We don't have p-values anymore. So we have this node 1 here, and then a root, and then the options. Okay. Weird, and then node 2, and then the options. That is not helpful. Let's maybe take a look at the summary of this, because I don't have a summary dot. Let's see, I don't think I do. Yeah, I don't have a summary dot tree, but I do have just the general summary function. Oops, and it's not called tree, it's called tree model. All right, does that help? Whoa, okay, so our regression tree, tree formula, okay, that's all fine. Variables actually used in the tree construction. Okay, this is interesting. It's only using 2. It has decided that the undergraduate GPA and the GRE of the GRE score are the 2 most quote-unquote significant predictors. Now, I'm not using significant in statistics terms, I'm using it in the English way, that these 2 variables are the most, they contribute the most to the outcome, okay? Number of terminal nodes is 8, residual mean deviance, okay, whatever, and then the distribution of the residuals. Now, residuals are still calculated in the same way. We have our predicted values, or the fitted values, we would say, and then we have the actual values, right? And it's just the predicted minus the actual. And we can plot them too if we wanted. But what I actually want to do is I want to plot the actual decision tree, okay? So we have a ton of variables involved, but we don't have to worry about plotting in a bunch of different dimensions because we're not in the world of linear regression anymore. This is a non-parametric test, non-parametric tool. So the only downside with this, and it's not much of a downside because there's still packages out there that make it look pretty, but it's the easiest to plot in base R. And so we just use this plot function, and then we put in our model, our actual model. And if I run this by itself, what do we see? Okay, we get this weird bracket kind of formation. But we'll see that that will turn into a tree here in just a second. So we'll just use a comma, and we want to use this type equals uniform. That's just a way of plotting. If we change that, we see now that it's all sort of standardized to the same size, right? It's not clumped up anymore. That's what that type uniform does. Okay, and then I have to use a semicolon to connect these next two functions together. This is just going to be text, okay, and then the text is just coming from the tree model, and then pretty equals 0. What this does is it just sort of unclutters a lot of the labels on the trees. The only downside is that it will just sort of arbitrarily pick ones to get rid of if they are cluttered. So there's a little bit of sort of prettying up that we have to do manually. Thankfully, in this case, we don't have to worry about that. And we get this very interesting tree, okay? All right, so here is how you interpret this. This is just an example, okay? So it kind of picks out a few of the actual values, it tells you sort of some of the most frequent predicted values, and we'll make a node out of that, okay? And then after that, it will terminate at these little leaves down here. So every last value that you see here is known as a leaf. Everything here where there's a split happening is known as a node, okay? So this is our first node. This is our root node. And then the things that connect the nodes together are branches. Here we are, we have a tree, okay? It turns out these are actually very interesting because decision trees are actually very similar to how humans make decisions themselves, right? Sort of unconsciously. We sort of do this yes or no, does it meet some criteria? If it does, okay, then do something else. That's sort of the way that, very generally, very basically, our decision-making psychology works, which I think is interesting that we're able to sort of use that in statistics, data science too. Okay, so anyway, how do we interpret this? Well, let's take it one at a time. So what we have to do is we have to start up here at the very top. We have to start at the root node. And then the process sort of follows this structure. If the statement here is true, then you go left. If the statement here is false, then you go right. Okay, so is the undergraduate GPA less than 3.494? Yes. Okay, we'll go down here. Is it less than 3.2? No, let's say. Okay, then we go over here. Is the GRE score less than 316? If it is, then you say, okay, there's a 65.59% chance that you'll get into grad school. If it's greater than that, and it's met these criteria here, then it's a 72.59% chance of getting in, okay? Pretty straightforward. You just have to make sure that when you're interpreting this plot, and I'll get to why this plot is actually not the most important thing to look at in a second, but you just want to make sure that you're saying, okay, if the GRE is greater than 316.5 and the GPA is greater than 3.2, but less than 3.49, then you have this chance of getting in. Let's take a look at the other end. Is the GPA less than 3.49? No, it's not. So we'll go over here. Okay, go down the branch and say, okay, is the GPA greater than less than 3.69? Okay, no, that's false. So then we'll go down here and say, okay, if your GPA is greater than 3.69 and greater than 3.49, which 3.69 is, then you have a 92.72% chance of getting into grad school. If it's not, then you say, okay, it is true that my GPA is less than 3.69. Come down here. Is it less than 3.542? Yes. Okay, then you have a 75% chance of getting in. If it's greater than that, but less than 3.69, it's 82.82% chance. Okay, so these values are just kind of randomly picked based on the most frequent occurrence of them in the training data set. Okay, sometimes that's not very helpful just to have these, right? Because we know that this whole thing is on this sort of continuous scale. So the big thing with data science and the big thing with these tree-based models is that you don't really have to look at the plot to get an idea of what's going on. What we do instead, and with data science, is you just make the model and you optimize it as best as you can, and then that's it. You use it for prediction. You give it as a data scientist. You would make data scientist. Good Lord, you would make a model, optimize it, and then give it off to the the back end developers of some website or whatever, or the marketing team for the business that you're working with, and then they're able to sort of make it work based on whatever software they have. Okay, so when we're looking at this like sort of visual representation of the model, it's not the most helpful because it just sort of arbitrarily picks the terminal leaves. Okay, so leaves, not leaves. Okay, so the idea here is that we want to optimize, right? Let's actually check. Let's check the residuals. Okay, so the residuals calculated in the same way, but what I want to do, I'm going to kind of section this off. What I want to do is I want to save the residuals of this model as resid, and then the tree model. Oops. Okay, so I do that, and that's just going to be, 320 objects here. That's all fine. That's all good. And then I'm going to plot these just to see how they're doing. Again, residuals don't need to have any kind of distribution or whatever. They don't need to be totally perfect because we don't care. The model is sort of robust enough to account for clumping in one side and not in the other. So what I'm going to do, I already have this written up. I'm just going to copy and paste this over. And I'm going to run that. So what this is doing, I'll run it first. I don't want to use any data, so I've just put that as null. And then the x is just going to be the 1 through 320, right? The length of the residuals. And then the y is going to be actual residual value. And then blah, blah, blah. This is sort of manually making that versus fits, or the fitted values plot. Because the autoplot function does not work for the residuals with this tree-based model. It just doesn't, so we have to do it by hand. Thankfully, again, doesn't really matter. But here's what it looks like, right? We see that the residuals, regardless of where you are in the data, are pretty equally scattered. That means that it's doing a fairly decent job. That error term is totally significant, or totally consistent, we'll say, throughout. Again, we don't really care. This is almost expected with decision trees to have a fairly equally scattered residual plot. But just sort of as a comparison, we see that the model is doing fairly decently. Okay, so the whole deal with this is to predict some new values, okay? And so there's a few things. The first thing is what I mentioned earlier, is that essentially we're just going to be doing prediction with these models. We don't have to plot them and make them look pretty or whatever. We just have to optimize the living hell out of it. Okay, so the second thing, let's see. Yeah. is now we're going to be using that testing data that we had. So we used training data to make the model, and now we're going to be using new data to test it, to see how well the predictions are doing. Again, we're not using residuals in this case. We actually use what's called mean square error instead of residuals, because the pattern doesn't really matter to us. But what we do want is the smallest MSE, mean square error. So what we need to do first is we need to make a predicted values data frame. Tree predicted, okay? And we're going to use that same predict function here. And the object is going to be our model. And then the new data, this should all be kind of familiar. You've used this a few times. The data is just going to be our training. No. It's going to be our testing data, okay? So the testing data, we'll take a look at it again, has all of the variables and then the chance of admit. When we put it in the prediction function, it's going to ignore this, so it's not going to use it in the prediction. So just, FYI. Anyway, so we do that and we save it. And now we see that we get a vector here of predicted values, okay? And it's 80 of them because we have 80 values in our testing data set. So what I want to do is we could calculate the residuals, quote unquote, by hand. But we don't really care about what the residuals are looking like. But what we do care about is the mean square error, okay? So we do that by saying, okay, take all of the predicted values that we just did. Take all of the predicted values and then subtract it from the actual values that we have. So it is still sort of the same way of calculating the residual, but we're sort of doing it in a slightly different way, okay? Because we're just going to get one single value. So this is our predicted values. This is the actual value, right? So if we just run that, we'll get a bunch of, actual probabilities, okay, from the testing data set, and then we'll just square it, like so, okay? And that's that. There might even be a function MSE, but anyway, so what this is saying, we get this value of 0.006. What that's saying is that the mean square error is, 0.6% wrong, more or less, okay? When you get into classification trees, it's doing the same thing, but instead of looking at a continuous outcome, it's looking at a 1 or a 0, like an event. Then the mean square error you get would be more or less like how often it misclassifies. Very interesting, right? But in this case, we'll say that less than 1% of the time, or we'll say that it's wrong more or less by about 0.6%. So very small, which is awesome for us, which is pretty great. One thing I do want to see. Yeah, there's no mean. What is this? No, not what we want. All right, whatever. I'm just curious. Okay, cool. So we've got all that. What I want to do next is we can make a plot. We can make a plot out of the predicted values and the actual values. Okay, we're not plotting the residuals, but we're just going to plot the actual versus the predicted, and we'll see how they kind of behave. So I'm going to make this comparison data set. I'm going to call it comparison, and it's going to be a data frame, and it's just going to be the actual. So the testing data, okay, with the testing outcome, and then the predicted. Now these are just going to be the the column names. So I can even just do this, put them in quotes so we're not confused. And then we just take the predicted values. Cool. Run that. We can take a look at it if we want. We'll get 80 values of the differing row names or the row numbers here. And we can kind of see that, more or less, like this 0.76, 0.82, that's not too far away. 0.75, 0.72, that's decent, right? 0.45, 0.72, that's not great. So on and so forth, right? So what we can do is use Ggplot to plot the actual versus predicted. So I'm just going to copy and paste this over from something. that I already had. So we see the x will be the actual and the y will be the predicted. We'll run that and we'll zoom it in. And I've kept the lowest line smooth because we don't really care about how well it fits a straight line. We just want to see sort of how it's behaving overall. And we see we sort of get this like step function almost, right? So like this one down here, this actual value is like 0.4, whereas the predicted value might be a little bit less or a little bit greater. But we see that everything is more or less doing fairly decently. If these were like super spread out or like very far apart from the actual, then we would have an issue. But for the most part, everything here is behaving fairly decently, right? And we saw that with the mean square error, it's less than 1%, right? So which is awesome, which is super great. Okay, so what we want to do next, though, is that we want to validate this model, okay? How do we do that? Well, we're going to do what's called k-fold cross-validation, okay? And what that does, it sounds interesting, it sounds difficult, but it's not too bad if you can imagine it. So if you imagine that you have like 10 coins in a row, and you make, that represents sort of your data that you have. And then you have some model, right? And you have these 10 coins that represent 10 observations based on some model, okay? And then what k-fold cross-validation is doing is it's taking one of these observations out at a time and just seeing how the model changes when you remove one of those. And then it'll do it again for the next, and then do it again for the next. And then after that, it'll start taking out different combinations of observations, and then do it again and again and again until it exhausts itself. Okay, so again, not too important how the math works out. But what we're going to be doing here is using cross-validation, this k-fold cross-validation, to prune our decision tree. Again, these are legitimate terms. I'm not making this up. So I'm going to make a new data frame here, and it's going to be made up of the CV tree function. And what it does, and we can kind of read about it here, is it runs a k-fold cross-validation experiment to find the deviance or the number of misclassifications as a function of this complexity parameter k. Okay, so it's going to be doing the first thing. It's going to be looking at the deviance rather than the number of misclassifications, which is fine, right? Okay, so we put just our tree model in here, and I'll be specific. It's the object. So if I run that, it makes this a list, right? And then it's got a bunch of different stuff in there. Who cares? But what we want to do next is that we want to plot. Oh man, okay. We want to plot that deviance and then the number of terminal leaves. Okay, so it's kind of similar to the like the best subsets graph that we got. So it takes all the best subsets of various variable sizes, right, or subset sizes, and it sort of plots them based on whatever parameter you want. We used BIC and R squared. This is doing the same thing, except it's instead of using R squared or AIC, it's using deviance. And then it's plotting on the x-axis, or we'll tell it to plot on the x-axis, the number of maximum leaves, okay, terminal leaves. So we'll put in our list here, and then the x variable is going to be size, right? And that size just represents the number of leaves, okay? And then y here is going to be the cross-validated test here of the deviance, okay? And then type equals b. Now, this is a base R plot function. This is not Ggplot or anything like that, so it looks simple, but you do have to add in these extra little things to make it look, readable. So let me make a little note of this too. This is our deviance, okay? So if I plot this, forgot a comma. Oosh. All right, we'll zoom it in. What do we see? All right. So we see here that the deviance, right, is here on our y, and the number of leaves that it ends with is here on our x. Okay, and the idea here is that you want a model with the least amount of deviance, right? We're sort of optimizing it for that. If you were to plot this and then, you know, kind of look for the smallest deviance, we might have 7 or 8 here, sort of a tie. It might even be that, you know, these are almost the same. It looks like 8 probably has a smaller deviance, just a little bit. If we wanted to, and we can, and actually we'll do that in a second, but what we're going to do is we're going to take the derivative of this function, and we're going to see, and we're going to set it to 0, essentially where the minimum is, which is fine. Again, we're not going to do that by hand, thank the Lord. We're going to let the computer do it. And how it's going to do it is going to use this which.min function. And we want to see, we want to see which deviance is the smallest, right? And we'll see that, okay, the smallest deviance is 1, which is great, right? On the scale from 1 to 7 over here. And then what we want to do, if we were to use this which.min on the cross-validated, for the size, it'll just give us 8 here, which is saying that the smallest deviance size based on the x value is here at 8, right? And we sort of saw that, right? So that's all good. That's all fine. What I want to do then, this does get kind of complicated. So this is the smallest overall deviance included, which is 1, and then this is the smallest deviance given the size, right? Which is 8 here. Cool. What I want to do is I want to save that, or just sort of see how that can be used to optimize our model. And I think it turns out that we can, let me plot this again. I think it's already using 8 here. 1, 2, 3, 4, 5, 6, 7, 8, yeah. So it's already as optimized as it can get. But let's just go ahead. I'm going to do it for you so you can use this in the future. But if I do this, I'm going to copy and paste this over. What this is doing is taking the size. It's looking at the size, right? So 1 through 8. And then it's going to select the one with the smallest deviance here, which is what we're doing with the bracket situation, right? So this is just saying, this is sort of, both of these are doing the same thing. This is the one that you want to use, though, because this is going to be the more generalized version. So use this for smallest deviance. Cool. Same thing for classification trees too. When you get into that, I won't go over that because that's actually a whole class on its own. So okay. Anyway, here we go. We're actually almost done here. So what I want to do is I want to make a new. I want to the best optimized, right? Optimized model. And we're going to do that by pruning it. Okay, so this is going to be our pruned model. And we're going to use one last new function, and it's going to be prune.tree. And this is all part of the tree package too. Okay, so this tree equals, and the tree is just going to be our original model, right? Our original tree model. And then the next thing we use is just going to be the best. Okay, so it's going to be, we have to specify which number of terminal leaves it needs to use, or needs to plot, and we'll just use this thing that we got up here, right? So this is going to say 8. It's going to make 8 nodes. We could also just put in the value 8, but that's not very generalized, right? So we'll just use this for now. Run that, and it's all good. Okay, so now let's plot it. Again, we'll just do the same stuff that we did earlier. Type equals uniform. If we just run that by itself, we'll see we're actually just going to get the same. We're going to get the same model that we got above, but we know we have validated that it's the most optimum, right? Hello? going on? Pruned model, dummy. Okay, cool. So we'll see that this is all the same, right? This is all the same as before. Even the predicted values and stuff that we get is going to be the same. So what I'll do is I'll copy and paste all of this back over, just so you have it. But I want to make another one of leaves 7. So those the number of terminal leaves. I'm gonna just quickly do this, and then That's all fine. That's all good. So it's still doing all the same. That's all good. Word. All right. So let's say 7 terminal leaves. Okay. So I'll just come back up here, and I'm going to take this code and just see how it changes, right? So I'll just call this 7. Not the most specific, but we'll just put 7 in there too. And then I will grab this, and then I'll put 7 in here and 7 in here, run that. Okay, and now we see that we get a plot here, a new model with just 7 terminal leaves instead of 8, right? And it's about the same if we were to kind of put them side by side, but you know, really whatever, because we know that this is not the most optimal. I just wanted to show you sort of how things change. Now, one last thing that we want to do is we want to compare the models, okay? Comparing models. Okay, cool. And so this is kind of tough because, sure, we're measuring the same thing, but now we're comparing models. I want to compare the linear regression model to our decision trees. It's kind of difficult because we're using 2 different types of models, right? Decision trees are non-parametric and linear regression is parametric. So we can't use AIC or BIC or anything like that. At least I don't think we can for BIC. Let's see. Yeah. And the reason is because AIC, BIC uses what's called a log likelihood to calculate one of the values. And that's very much a parametric calculation, right? It kind of assumes some kind of distribution. With decision trees, since it's an algorithm, there is no distribution that it follows, right? So there's no log likelihood. So I'm going to use mean square error to calculate, sort of how well each model is doing. We already know it for all of the. So we already know it for all of our decision trees except for the 7th one. Let me do that real quick. So I have to make predicted 7. New data. New data is our testing data. Cool. All right. So our predicted 7. Sorry, I should have done this earlier. Definitely not going to edit this out either. So sorry. And then our our testing. It just takes so long to edit these videos. I wish I had like a professional editor or something. All right, cool. So we see that honestly, the MSE here is not that bad either. 0.649, whereas for our optimized model it was 0.60, right? So it's gone down, good Lord, just a little bit. But, all right, so, sorry. Let's go ahead and compare the MSE of all of these, just so we can kind of see which one is the most appropriate, right? So we want to make sure that we get the smallest MSE, and then we'll say that that's the best model, quote unquote. So I'm going to say MSE. I'll say Mse Comp Comparison, and that's going to be a data frame. So our linear regression is going to be, okay, here we go. It's going to be the mean. Let's see. How do we do this? What's the best way to do this? I guess I didn't predict that either. Let me do that. and I didn't split it up into, here's actually what I'm going to do. Since I didn't split this up into training and testing, what I'm going to do is I'm going to square the residuals because it's essentially doing the same thing. Square the linear reg model. So that's going to be all positive values. That's all fine. That's all good. I'm going to call this linres. Cool. All right. It's all fine. And I'm going to take the mean of that. Okay. And then I'm going to put our tree model. That we know that that's the most optimized. So I'm just going to go actually over here and just copy and paste this. Oops. I'll run that just to see. Cool. Oh yeah, this is cool. I love this. And then sev. That's fine. All right. And then we'll come over here. Now let's take a look. It's actually really interesting what I think is going on. So let's kind of review. Let's take a couple of steps back here and look at it from the bird's eye point of view. So our tree models, both the optimized tree model and this one with 7 leaves instead of 8, that's going off of 80 observations, right? Because our testing data is still decently big, but it's only 80, right? That's how we calculated the mean square error. And it turns out that the mean square error is a function of the sample size, right? The calculation for the mean square error is has got n in there, okay? And the mean square error will go down the more observations you have, okay? It's almost kind of like r squared, almost. Okay. And then we see that the linear regression mean square error is it's a little bit less than the two decision tree models. Okay. That's because it's using all 400 observations. And we know that if we go back here, let me do this too. So this is what our residuals looked like, right? We have tons of data that are fitting around this line really well, but the further you go down it, when you start getting to the lower scores, lower GPAs and lower GREs and whatever else, then the model becomes way more uncertain, right? So a lot of the work, a lot of the mean square error, the reason why it's so low is because so much of the points are so close to the line, right? Okay, let me also look at the model output here too. So technically, without looking at the residuals, everything here is statistically significant, right? But we can't really use this model because the residuals look like garbage, right? They haven't really met our assumptions. But the nice thing about decision trees is that you don't really have those assumptions. You don't need the residuals to look super decent in the first place, right? Because it sort of accounts for that. Comparing the linear model to the decision trees, right? So sometimes it makes sense to do regression. Oftentimes it's the easiest because straight up, this is all we had to do, right? Make the model, summarize it, look at the residuals, and that's pretty much it, right? We have all of this. We have all of this to do for the decision tree stuff. So it's a little bit more work, a little bit more time intensive, but you can make a hell of a prediction model with these decision tree stuff, at least. So with that, just a super brief introduction into decision trees. There's a whole lot more that goes on in a decision tree and making all of the models and whatnot. But for now, we'll call it there because we're going to get into random forest regression too. So it's essentially decision trees, but more of them. It's a ton of decision trees. It's a forest of decision trees, which is pretty cool. So I will see ya. I guess just when I see ya. Thanks for watching. Take it easy. Bubba's not in this one because it's not required for him to be here anymore. So, all right. See you later.